So here we're interested in developing a model for the power generated by an IC or internal combustion engine, shown here. And we're asked to draw an appropriate control volume that one could use for applying conservation of mass and the first law of thermodynamics in order to relate the power generated by the engine to other relevant parameters. So we're trying to do an engineering flow diagram, really, or an energy flow diagram for the engine. So we want to just keep track of the mass coming in and out of the engine, as well as the energy exchanges between the engine and the surroundings. So the way we're going to draw this is I'm just going to draw the engine as a block here, just to make it an easy schematic. And I'm going to draw a control volume around the engine, and then just schematically show the different mass and energy transfers occurring with the engine. So one of the things that we have is air and fuel coming into the engine cylinders. That's what's ignited in an internal combustion engine to cause the cylinders or the pistons to move. So I'm going to just draw that like this. So here's the mass flow rate, m dot, that's the mass per unit time, of the air and fuel coming in. And then once it's ignited, that air and fuel mixture is exhausted from the engine. So it's moved out through some valves. So I'll just draw that as an m dot exhaust. Okay, so this is the air and fuel coming in, gets combusted, and then the exhaust goes out. We also have some oil that comes into the engine to keep everything lubricated, so I'll just draw that this way, m dot oil coming into the engine, and then the oil goes back out. Oops, that should say oil, not out. So you notice that I'm drawing arrows to indicate when it crosses the control surface coming in as well as going out, and then just identifying what it is I'm talking about here. So oil comes in, oil goes out. You also have coolant, so the engine doesn't overheat. So there's some coolant coming in. There'll be some coolant going out. And those are the, as far as I'm aware, all of the mass exchanges with the engine and the surroundings. So air and fuel coming in, exhaust going out, oil coming in, oil going out, coolant coming in, coolant going out. So then, as far as energy exchanges, the engines get hot, right? I think everybody is aware of that. So there's going to be some heat transfer to the surroundings. So I'll just draw that as Q dot. That's just the heat. It's really energy leaving the engine in the form of heat transfer to the surroundings. The other thing that we have coming out of the engine is shaft work. So I'll draw that like this. I'll just write it as W dot shaft. The whole point of the engine is to rotate a crankshaft that basically turns a shaft that ultimately turns the wheels of the car. So we're trying, this is really what the goal of the engine is to get as much shaft work out of the engine as possible. You want to minimize how much fuel you have to put into the engine, but you want to maximize how much power you get out of it. In steady state operation, you would expect the mass of oil coming in to equal the mass flow rate of oil going out. Same with the coolant. You don't want any coolant, stuck in the engine. Whatever comes in goes right back out. As for what you'll learn with the first law of thermodynamics is ideally you would minimize the heat transfer to the surroundings as well, because any energy lost here is energy that doesn't go into the shaft work. So you'd ideally want to minimize that so you can increase this. But this is everything in our energy flow diagram. And once you have this, you could then start writing out the equations for conservation of mass and the first law of thermodynamics, or the second law of thermodynamics for that matter, and do further analyses. But this is the starting point. You really need a diagram like this to illustrate what all you have to factor into your equations that you use for your analysis. Okay, we'll end the example there.